So today's webinar is going to be about managing the quality ecosystem, Rhapsody, Simulink, and Modelica. We are having with us Fabio Di Nino. He will introduce us the concept of process needed to describe a real scenario where, while working in a model-based project using Rhapsody, there is the need of writing high-quality requirements concerning the UML, SysML elements of the project. Let me introduce your presenter a little bit more in detail. Fabio is has a Master of Science in Software Engineering, and he is software analyst at the Reus company. And specifically, he is the analyst behind the integration of the TRC tools and IBM Rhapsody, bridging the gap to interconnect them and creating the solution he is going to show us in this session. Reus company has its headquarters in Madrid, Spain, and also it has offices in London and Stockholm. And finally, we have partners all around the world, especially in Europe, United States, and Asia. Our main customers are in the field of aerospace and defense, for example, the companies members of the Airbus group, and automotive and energy, among others. The solutions we are showing you are part of the TRC suite. The TRC suite is composed of several tools around the same technology based on natural language processing techniques and system knowledge repositories. The first tool is System Quality Analyzer, which is in charge of the quality analysis of your specifications. It doesn't matter if are requirements or model simulation, etc. Then it comes RAT, or Rich Authoring Tools, which enables you to smart author your items such as requirements or models, etc., etc. Then we have a tool which is System Knowledge Manager, which is working all the parameters behind the scenes of these natural language processing algorithms. And finally, we have System Interoperability Manager, or SIM. The SIM is in charge of transforming requirements into another requirements, or creating traceability among all your elements, such as requirements and models, and so on. So now it's the time for Fabio, so welcome and thank you.
Hello everyone, this is Fabio Di Nino speaking. Thank you, Luisma, for the introduction. I start with what we are going to see today. I will briefly introduce RAT for Rhapsody, Rich Authoring Tool for Rhapsody, and then we will see two main subjects. The first will be UML SysML models, so how create and edit Rhapsody's requirement using Rich Authoring Tool. Especially we will talk about hyperlinks and patterns. And the second part, we will focus on physical models. Especially, we will see the FMU format and what we call executable requirement. Okay, the three main actors of today are Rich Authoring Tool, that we usually call RAT. For who doesn't know it, it is a tool that helps the user in writing a requirement on the fly. Especially, it's able to tell you the quality of the requirement on the fly. We will see the term assistant. The term assistant is a little window that suggests the words to use inside the requirement. And finally, we will see the usage of the patterns inside it. Then the central actor is IBM Rhapsody, because everything, you will see that all the interaction will start inside Rhapsody. Rhapsody is a professional tool by IBM to model UML and SysML diagrams. And finally, we will see FMI FMU format, that is a physical model format for simulation. So I spent a lot of nights working on it, so and I want to make this presentation as much fun as possible. So the three actors will be three puppets. The first, obviously, is a rat for rich authoring tool. The second one is a panda for IBM Rational Rhapsody. And finally, we have a fox for the FMU format. They will help me inside the presentation. Okay, let's start with a little bit of theory. I think that everyone have already seen the V process. What is important inside the V process is that usually we see here three different and separated phases. The first one is the requirement, where we start from the stakeholder requirements, go through all the sub-phases until the functional requirements and so on. And then one that the requirement phase has completed, we start with the modeling phase. And finally, there is the verification and validation phase. This is the theory. The real world, we know that these three phases are always somehow merged together, interconnected together. They are not really separated. And here comes our solution. We want to, first of all, we will see that this solution is done to be used inside a model-based project. So where the model is the center of the description of the model, and the requirements and the models stay together in the same environment, but also we want to anticipate as much as possible the verification and validation phase to be able to check the feasibility of a requirement inside this model-based project. And here are our three friends in the three different phases. Okay, now I have a question. Why models, in this case diagrams, need requirements? As I said, usually the requirements phase, we write all the requirements and then we start the modeling phase. But here we are going to merge these two phases. Why should, I repeat, why should models need requirements? To answer it, I took a sentence that I really like from requirements engineering book of Hall, that says that a particular model never says everything about a system. If it did, it would not be a model. If you think about it, when you describe a project, a new product with diagrams, you usually use different diagrams. You can use class diagram, sequence diagram, state chart, use case diagrams. That's because the diagrams only describe one phase of your project, of your new product. So you already need different models and different diagrams to describe the same product. What the requirements are able to do in this scenario is to fill the gap between these diagrams. And as I said, the solution that we propose is to use the rich authoring tool as a plugin on top of Rhapsody. If you're wondering what is this image, is an image again from the requirements engineering book, is the so-called system engineering sandwich, where really describe how the layers of requirements and modeling stay together in the same environment. Okay, what is important here is that we are going to have two main sources to write our requirements. The first source is the knowledge manager. For who doesn't know knowledge manager, that is a tool from the TRC company. It it is a tool to manage an ontology. So some terms of the requirement will come from the ontology. But also as I said, we are in a model-based situation. So some other part of the requirement will come directly from the diagrams. In this case, from the diagrams inside IBM Rhapsody. So all these terms and these diagrams element will be imported inside the rich authoring tool that will help us to write the requirement. What is important to connect? I call it the connecting point between the requirement, so the natural language and the models, is the hyperlink. The hyperlink is able to keep us in a in a text format. In this case, is HTML, but it is still text, but where we can refer directly to elements of the diagram. So, as I said, IBM Rhapsody sent to RAT all its elements, and and we use RAT to write the requirement, and the requirement is sent back to Rhapsody inside the diagram where we called the plugin. The second part, the second element that we need is the pattern. For instance, the pattern that I'm showing now comes from the ISO 29148, and for who doesn't know what is a pattern, it simply is a sequence of slots where where every slot has to be filled with a correct word to write a good requirement. In this case, for instance, the first word of the requirements that will follow this pattern is always when. But then we have an event. An event can be different words and different cases. Another slot can be a verb, a noun, and so on. So usually when we use a pattern, the information, the terms that we use come from an ontology. For instance, when then can be a noun, a verb, and so on. But what about the diagram's elements? The diagram's elements are not verbs, are not noun, are not adjectives. We are talking about classes, states, actors, and so on. So what we have done is to be able to define a slot of the pattern as a type or a stereotype of UML or SysML diagrams. What does it mean? If you take this example, that is the pattern that we will use in the demo, the second slot that you see is the class cluster. A cluster is a collection of terms, or in this case, is a collection of diagrams elements. So when we will write the requirements and comes the slot class, all the classes of the diagram will be shown to who is writing the requirement. This just to be clear, if you see the fourth slot is a visualization cluster. It means that inside this cluster there will be some verbs that are, in this case, about visualization that comes from the ontology. If we take the last slot here, is the actor slot. So in this case, all the actors present inside the project of Rhapsody will be shown to the user. So well, here, Rhapsody sent to RAT all its elements. RAT organized them inside clusters on the fly. Okay, finally, we can go into the video. Here we are in a model-based situation where we have an electrical bicycle project. We have different diagrams to describe it. For instance, here we have a class diagram. Inside the class battery, we have a state chart with the different states of the battery. And also we have a simple use case diagram. What we are going to do here is to write a requirement inside the class diagram to add information to this diagram. As I said, to fill the information gap of these three diagrams. So we right-click, we select RAT Smart Authoring Tool, that is our plugin, and we select Create a New Requirement. As you see, RAT starts. As I said, all the elements of the ontology and all the elements of the Rhapsody are imported inside RAT. Here we select the pattern, and you see that the term assistant starts to suggest to us the terms and the elements to use. So when, then an article. And what is important here is that the third slot is a class cluster. So all the classes that you see on the left side are suggested to us. Then there is the verb. We keep follow writing the requirements. Here there are the states of the battery. And now it will come the visualization. There is another time a class cluster. In this case, we select display. You see that when we insert the I want to stop 1 second here. When we insert a class or an element from Rhapsody, it is inserted as a hyperlink because, as I said, we want to refer directly to that element. And I'm going back a little bit. Okay, shall. Here you see this is a what we call a normal cluster, a cluster of verbs, in this case of visualization. That comes from the ontology. Okay. Here there is an attribute, for instance, the battery level that you see on the left side inside the battery. And finally, we have the actor cluster. So the cyclist and the technician are shown and suggested to us. We finish our requirement. We completed the pattern, so we can save and close, and the requirement is sent back to Rhapsody. We decide to draw the dependencies, so it is even more visual. And here we have our high-quality requirement inside the diagram. I just want to underline that if you click on one of these hyperlinks, let's say automatically Rhapsody bring you to that element. So that's why I say that in this case the requirements are able to fill the gap between the different diagrams. You see here in one requirement we refer to elements of 3 different diagrams, and we can navigate through the elements that we used. Okay, here there is the second part where we add the physical models. In the first case, we just deal with diagrams, so UML and SysML models. And here we also introduce physical models. How does it work? We use the FMU FMI format. I will give you some more details about it, but what is important is that, as you see on the left side, doesn't really matter which tool you use to create your physical model, but you have to be able to export that physical model into the FMU format. Then we will parse the FMU file inside the knowledge manager. So let's say that we will extract the information of this physical model and we will put them inside the ontology. So from the ontology will come the terms as normally, but also the physical model elements. And again, we are in a model-based situation, so we will have the diagrams elements from Rhapsody. We will use all this information, so the information that comes from the physical model, the information that we have in the ontology, so the terms and the information of the diagrams, again to write a requirement with RAT. Okay, if anyone has never seen or doesn't know what is an FMU format, from my point of view, the easiest way to see it is to compare it with a PDF format. Nowadays, all the document can be exported to PDF. More or less, is the same concept that the guys of Modelon applied to the FMU for the physical models. So, doesn't matter the tool that you use to model your physical model, but you want to have a common way to share to export your physical model. Let's go a little bit into the details of it. So first of all, the FMU can be seen as a black box. It actually is a zip file. It is a black box because you can only see two parts of it. The first one is a description, so it tells you the inputs and the outputs of the system, and the second part is the simulation. So you can actually see the input, change the inputs, simulate the physical model, and to see the output of it. But you cannot really see, for instance, the equations or how it is implemented. That is why it can be a black box. Okay, this is another pattern that we will use in the video, where again you see the first slot here is a class cluster as we used before. So the information in this case will come from Rhapsody, but the last slot here is a FMU model variable. So this cluster will be filled with the information that comes from the FMU file. Okay, here we can show the video. So here on the left side we have a very simple physical model of a rocket done in this case in Modelica. But as I said, the important thing is that we are able to export it into FMU. Here we open Knowledge Manager to parse that file, that physical model. So here I use the index option. I don't go into the details of it, but because there will be a webinar about the parsing and the indexing part. But as you see here, I select the rocket.fmu file to parse it. And here are the information that that I'm able to extract from it. Here are all the, for instance, all the inputs and the outputs of the file. The second phase is to write the requirement inside Rhapsody. So again, we right-click on our diagram, that in this case is very simple. It just has one class called Rocket, and we start to writing a requirement using Rat. So I leave on the right part the the two other sources, so the Rhapsody and the ontology, and on the left side we start to to follow the requirement. You see the second slot here is a class cluster, so we insert Rocket as a hyperlink. We keep follow the pattern here, and you see there are different slots with numbers, unit measurement, and so on. Here we are writing the condition. And here I want to stop because here there is the important part. You see here that this lot suggests to us the information that we parsed from the physical model. So we have, in this case, all the inputs and the outputs. Well, actually, they are the names of the variables that we extracted from the physical model. So we finish to write our requirements, completing the pattern, and again we save and close the RAT, and the requirement again is sent to Rhapsody. Okay, let me pause just 1 second here. I need 1 second. Okay, the second part of the video, as I said at the beginning, is about the simulation of the same physical model that we parse. What does it mean? At the beginning, if you remember, I said that we want to anticipate as much as possible the verification and validation phase. So now what we are going to do is to use the same physical model that we parsed to see if what we have written inside the requirement makes sense. So to be technical, is feasible against the simulation of the physical model. So here we use another feature of our plugin. So we right-click again on the requirement, and we use the command execute selected requirement. This is why we call this kind of requirements executable requirements, because we can somehow extract the information from the requirement and simulate it using the physical model. So here, as you see, we have the the text of the requirement. We have to select again the physical model. You see, when we import the the physical model, when we load the physical model, again all its variables, all its input and outputs are shown to us. And here we want to get the information. Let me stop 1 second here. We want to get the information from both from the requirement text, but also from the diagram. You see that in this case we extract the initial height from the requirement text and the initial velocity from Rhapsody, from the rocket class in this case. What does it mean? It means that we are going to simulate, to do the simulation according what we have written inside the requirements and inside the diagram. And also, if we it's not in the video, but in this phase, you can also insert your input. So if I want, for instance, to change the initial launch angle that by default is 45 degrees, I can change here just clicking on 45 and insert the angle that I want. Okay, I set up everything for the simulation. I select what we want to see, what we want to plot. Here I have to manually define the condition that actually is defined in the in the requirement. So the height shall be greater than 300 meters, and we can finally simulate the requirement. First of all, it says the condition is satisfied, and then it shows to us the plot. You see that the rocket actually goes above 300 meters. And at the end, we can save and close this window. And you see that due to the fact that the condition has been satisfied, we also paint the requirement in green. That's because we want to have a graphic visualization of our requirement. In this case, this is green light. It means that this requirement has been tested against the simulation of a physical model. Okay, just to conclude what we have done in the last part of the video, we have the information that were coming from the requirements and the rocket. On the other side, we have the physical model, and there are the three phases. We get the input that can come from the requirements, from the diagram, but also, as I said, on the fly, you can insert the inputs inside the window that there was in the video. Then there is the simulation of the physical model, and finally we have the output. The output is the feasibility of the requirement, and we paint our requirement accordingly. Okay, the last amazing animation. Here, Rhapsody sent to RAD all the information. RAD sent back the requirement, but is the simulation of the FMU that defined its feasibility. Thank you for your attention.
Thank you very much, Fabio. It's been very interesting to see how these tools can work together in our engineering environment. Now, if you have some questions, please write them down in the chat to the RIS Company user. While you type these questions, I would like to introduce our next webinar. The topic for it will be assessing requirements quality against logical and physical models in Rhapsody and Simulink, and ontologies in Protege. Okay, a little brief description of the webinar will be that in the world of model-based system engineering, we usually find a huge ecosystem full of tools. The community of practitioners will be using a wide variety of different tools for requirements management, logical and physical modeling, traceability, simulation, quality management, etc. With regards to quality management, System Quality Analyzer (SQA) performs requirements quality assessment based on the correctness, completeness, and consistency approach. That is, automatic verification of your requirements and support to requirements authoring. For this purpose, the SQA knowledge base ontology can be customized to automatically include in real time the content of the Rhapsody models or Simulink files, or even external ontologies created with Protege, among others, so that requirements quality can be assessed against all of those models. In addition to that, the knowledge about a project is a living entity. That means that it will evolve, hopefully, along the project lifecycle. An ontology configuration management process will be presented to keep track of the changes performed on the ontology. Okay, so let's see if we have some questions here. Fabio, how will this strategy work if multiple requirements are to be analyzed for feasibility by a single performance model?
Yeah, that's a really good question. Let's say that this is the first implementation of FMU and requirements. We are working on, so let's say that in the state of art of today, we are able to link just one requirement to one physical model. But the next step is that one that you suggest, to be able to link different requirements that obviously will define different information about the behavior that has to follow our system, and to check all of them, or at least to use all of them against one physical model simulation. And also, on the other side, we are working on the possibility to have different physical models that are simulated one by one or together against the same requirements. So let's say the relationship, the first relationship could be n requirements against one physical model, but also one requirement against n physical models.
Thank you very much. Next question. How the hyperlinks are implemented, Fabio?
Okay, so the hyperlinks, I didn't go too much into the details, but the hyperlinks in our case are HTML text. So it means that if you know more or less how an HTML hyperlink is implemented, it usually has an address. So an address, for instance, to google.com. In our case, the address is the ID of the elements of Rhapsody. So, for instance, when we refer to the battery class, the hyperlink is created with the name of the class, so in this case battery, but also with its ID put in the address of it.
Okay. Let's say they are happy with your answer, so we follow to the next one. What do you mean with the elements of Rhapsody when they are imported on the fly?
Yeah, imported on the fly means that, let's say the scenario that we presume is that we are working on Rhapsody, so we are defining our diagrams. At a certain point, we want to write our requirements. It means that every time that we want to write a requirement, we have to be able to refer to all the elements of Rhapsody. So every time that we call rat, we import on the fly all the elements of Rhapsody. This is because when the user is working on Rhapsody, he can change the diagrams, he can create new elements, and so every time the elements that are imported have to be refreshed.
Okay. Now the next one is it working only for Rhapsody?
Today, this plugin is working only for Rhapsody, yes. but has been thought to to work also with other tools. What does it mean? That the interface that we use to communicate with RAT is ready to communicate with other tools. For sure, we have planned to implement all these features, the same features for Magic Draw, for instance.
And we have another question linked with this last one that you have answered, and they are asking how could this work with requirements created in DOORS for DOORS next generation? Can we map requirements in this tool to the model elements? What do you think, Fabio?
Okay, yeah, the DOORS part at the beginning is we thought to to put the DOORS part in this webinar, but actually we made a couple of tries, and to explain properly the DOORS part, there will be a webinar only about it. But to answer for your question, let's say that for the IBM DOORS, what we think that we are able to do is to, let's say, write, as we have done, all the requirements inside Rhapsody. Then we already have a feature that I didn't show to you in this video, but we already have a feature to collect all the requirements that we have written inside the diagrams, because you can think that if you are working in different diagrams in a big project, you probably will have all the requirements splitted in the different diagrams. So you don't have the usual sheet work with all the requirements in the same page, let's say. Okay, so we already have a feature to be able to collect all the requirements inside the Rhapsody. And to answer to your question, the next step will be to take all these collected requirements and export them into DOORS. So once that you have written all the requirements in Rhapsody, be able to export them in DOORS, or at least to add them to the other requirements that you probably have written in DOORS.
Thank you, Fabio. Hope this answer solves the question that we have. We have another question. Will that maintain or create OSLC links? Fabio, what do you think?
Okay, so let's say that OCLC links, in this implementation, when you see the hyperlinks and everything, we are not really talking directly of OCLC links. I cannot answer to you at. I'm not sure at 100% about what I'm going to say, but I really think that once that we define how to export these requirements, we will be able to define how the links, and in this case OCL links, will be maintained.
Okay, and I have one more for you, and it is: what about if we have a big diagram with hundreds of elements? What will happen?
Yeah, okay, this is a good question, because when I showed to you clusters and patterns and everything, obviously we were working in small diagrams. Let's put down a situation where, for instance, I have different class diagrams, and it is possible to have hundreds of classes. What we have done here is to be able to select, let's say, to reduce and to filter which elements are going to be imported inside RAT. For instance, we can say, okay, I don't want to refer to all the classes. I mean, in this requirement that I'm going to write, I don't want to refer to all the classes of my project, but also only to the classes of these diagrams. Usually, what happens is that due to the hierarchy of the UML and SysML diagrams, a specific requirement it's let's say define better something about one single element and its children inside the hierarchy. So as I said, this example is a diagram that owns all its elements. But another example is that I want to write some information more about a class. So I want to refer to that class and its attribute and its method, not to all the classes and attributes of the Rhapsody project. So as I said, what we have done is the possibility with another feature to limit, to reduce the elements that are imported into RAT, because as I said at the beginning, too much to show to the user too much information it's useless. We just want to show the important information that really help the user in writing requirements.
Any more questions? I think I have a last question. Okay, Fabio, this is the last question that we have here. The core of RQS, well, he means TRC suite, was KM. It's knowledge manager. It seems here that in the new revision of the requirements quality system, the TRC suite, that this code is distributed, allowing, for example, direct dialogue of the RAD with the Rhapsody of FMU. What do you think, Fabio?
Okay, let me just read again because I think it's complicated as question. So the core of RQS was the KM. Yeah, it seems here in the new revision of RQS that this core is distributed, allowing, for example, direct dialogue of RAD with Rhapsody or FMU. Yeah. So let's say that in the new version, probably Luis can help me. In the new version, one of the goals of the new version is to be able to connect to more sources as possible. I mean, in this case, I showed to you that the two new sources are Rhapsody and FMU, but we also have other sources, for instance, Excel or Papyrus and a lot of other sources. But yeah, let's say your question is correct. We try to we are moving to have one single static ontology that obviously is the core of the KM, to be able to import on the fly different elements of different sources.
Okay, I can add to the question that it is exactly what you say, the core of technology, that it is managing Knowledge Manager or System Knowledge Manager, as we rebranded it in the latest release of the suite. It is ontology, but we try to open these methodologies and these algorithms to all possible sources we have along the engineering process. Okay, so we have that ontology, we have algorithms, we have techniques, and we have a lot of different work products along the engineering process. So we try to address more problems because we have information to solve more problems, such as traceability, okay, or transformation of requirements with this technology. So this technology, as you said, is the core, and it is a little bit expanding the things we are using this technology to develop new smart things along the engineering process, and that's it. Hope this information helps you. Okay, do you have any other okay, thank you. Do you have any other questions? Thank you very much again to all the participants. Thank you very much, Fabio. Bye-bye.
Bye, everyone. Thank you.